Okay, hello everyone. We'll start a new week today and actually a new chapter. Today we're going to start chapter 3, and our treatment of chapter 3 is going to be different in the sense that we're only covering actually two sections, because as we very well know, 3.1 is usually an introduction and meant to, motivate what is it that we're studying on the chapter. And then we only have 3.2 and 3.3. And again, the issue is not that the other sections are not important or relevant. They are. It's just that we don't have enough time in the semester to see everything. And so the chapter is called Basic Topology of the Real Numbers, right? And those of you that are math majors and that will continue on to grad school will probably later on take a topology class where you will actually get to see many of these concepts in a more general setting. So this will actually be a great introduction. But nevertheless, even if you're just a math major, terminal degree math major, this is something that you should know. It should be in your general knowledge of as a mathematician, as a math major. All right. So as we usually do, we're going to introduce the subject by going briefly over 3.1. There are no exercises in section 3.1, but it is nevertheless actually a very nice topic. It's about a specific subset of the real numbers, which is very, very interesting, and you should be familiar with, even if you don't know anything about anything else. You should at least know about the Cantor set, which is what we're going to be talking about to begin with the chapter today. All right, so let me go to the page and we'll start talking about the Cantor set. The Cantor set. All right, and we'll go right away to the definition, and maybe some of you have heard, pretty sure of that, the term of a fractal, right? And you could think of this Cantor set as the grandfather, the grandpa of all the other more involved fractals that were discovered later on. You could think of this as probably among the first fractals that were created. So let's go right ahead and define it. So this is a subset of the real numbers, and in fact, it's a subset of the interval 0, 1. So it is constructed as follows. Okay, we will construct it in a way where we're gonna start with something and we're gonna prune it. So we're gonna take things out, and whatever survives is what we're gonna call the Cantor sets. Okay, so to begin with, we're gonna start with C0. So our first iteration, if you want, our first attempt at what we want this set to be. And this will be easy. This will just be the interval 0, 1. And I'm going to start a picture of the set right here on the right. So the closed interval 0 to 1. That's C0. Okay. Then here's what we're gonna do, and this is the process that we're gonna actually keep repeating. So pay attention. It's actually quite simple. What we're gonna be doing is we're gonna remove the middle third. Remove the middle third. So I'll explain it with the picture first. So here's C0, and if I look at this divided in thirds, this would be 1/3 and 2/3, right? Those are the numbers that divide this in 3 equal pieces. And what we're going to do is we're going to remove this guy in the middle. So our next iteration, C1, will be from 0 to 1/3. We remove the open interval, by the way, and then from 2/3 to 1. And this is C1. So C1 is C0. Take away the middle interval 1/3 to 2/3. All right, is that clear? Okay, and now that you learned it once, we're just gonna keep doing this. Meaning, for every one of the intervals that remained, so we have an interval here and another interval here, in the next iteration, what we're going to do is we're gonna remove the middle third. You get it? Let's do the next one. So C2 would be take C1, and we're gonna now take away these middle thirds. Two middle thirds. This one is from 1/9 to 2/9, and this one is, let's see, so this is these are 6/9, so this is 7/9 and 8/9, right? So those are the intervals we're taking. We're taking 1/9, 2/9, and we're also taking 7/9, 8/9. All right. So the new picture for C2 is from here to here, and then from here to here. And then here from 2/3 to 7/9, and then from 8/9 to 1. All right. My picture is obviously, I mean, this looks a little tinier than this part, but it's okay. You understand because I'm labeling it right on the x-axis. So this is C2. Okay, and so on, right? So we're going to continue doing this. So we're doing C3, C4, C5, C7, etc. And notice that what we have in this, so in general, Cn is obtained by removing the middle third of every interval in Cn minus 1. Those are the general recursive instructions. All right, so I'm not gonna mark the, okay, let's do one more. Let's do C3 here. So C3 would be from 0 to 1/27th, and then from 2/27ths to 1/9th. And then over here from 2/9ths to 7/27, and then from 8/27ths to 1/3. And then these ones I'm not gonna put the names of the, because it's just gonna take me too long, but you get the idea of how it looks like, right? And then we continue. So these little ones, we take the middle third away, and then, right? And so a name that you may hear when you talk about this set, they also call it Cantor's dust. Because think about it, what's gonna remain in the end? Okay, so first let's notice the following. Let's notice that C0 contains C1, right? Of course, because we just removed stuff, which contains C2, which contains C3, etc., right? So we can call C the intersection of all of them. So the Cantor set, we're just gonna call it C, and it will be the intersection of all of these guys, from 0 to infinity. In other words, the points that remain when we do all that removing. Okay. Now, if you've never seen this before, you're probably asking yourself the following question. I mean, is there something that's going to remain anyways, right? Will anything remain after all? That's the first question. Are we really going to have something in the end? Because, I mean, we're obviously taking more and more stuff along the way. So maybe you think that there's nothing when we're done. And so I'm going to start by showing you that that's not the case. So there are things that will remain. For example, think about 1/3. The number 1/3. 1/3 is in C0. And when we take away the middle thirds, it remains because it's one of the endpoints of the interval. So we keep it. And then when we take the endpoint of the next one, it's still there. And here it's still there. And it's going to be still there all the time, right? Do you all see that? Because when we take the next one after that, I mean, we're not going to affect this interval anymore. We're going to take the middle third of this interval, but 1/3 is far away from there. So in other words, once you're an endpoint of an interval, so we did 1/3, but we could have done any other here, 7/9. 7/9 will survive because here, when you take the middle endpoint of this one over here, the middle third, it will still be here. It will be this one over here, 7/9. And then if we magnify and we do it again, there will still be there 7/9. It was going to keep going no matter what. So you should realize at least that at least all the endpoints will remain. So let me just make a little note here. Note that the endpoints of the intervals along the process will belong to C. So there will be stuff at the end, right? Now, the intervals are not that surprising. The endpoints of the intervals, I mean, it's not that surprising that those guys survive. But there are others. There are others that are not endpoints, and they survive regardless. So, for example, a 1/4, the number 1/4 is, you don't see it here in this picture. So let me just write here. But there are others. E.g., 1/4. 1/4 belongs to C. And I'll tell you, I'm not going to explain right now at this moment why 1/4 belongs to C, but I'll actually tell you a bit more what are the numbers that are in the Cantor set. But it's a very interesting set, this Cantor set. Like I said, the picture is, we almost don't see anything, right? Let me see if I can actually show you. So if we look, hold on just a sec. I mean, it's hard to give you a picture because it's almost like dust, right? Nothing is there at the very end. So you start taking stuff. I mean, probably the better pictures that I have seen that try to explain what's going on look a bit like this one, and I'm going to show you in just a moment, which is essentially what we're doing right now. So let me show you. So it looks like this one here. So you start with the big interval. That's the big one on top. Then you subtract the middle third, so you have the second line, then the third line, the fourth. So kind of like the picture that I was trying to do by hand. But if you start doing a lot of iterations, you see that it starts looking like the last one over here, where you barely have anything, right? And that's the reason it's called the Cantor dust, because you don't see almost anything, right? In fact, let's try to do the following, and that's the first interesting thing about this set. Let's try to calculate the lengths of the intervals we're removing, okay? Let's do that. So let's go back to the page and talk about calculating the lengths of the intervals we are removing. Where's my... So let's calculate the lengths of the intervals that we're removing. What is the sum of the lengths of the intervals removed? All right, and let's start from the beginning. So what is the length of this first one that we remove here? That's easy, right? 1/3. So first we remove 1/3. Then we took away this guy and that guy. So there were two of them that we had to take away. And now the length of them was 1/3 of 1/3. So meaning 1/9, right? So the next one is 2. We removed 2 of them, and each one of them was length 1/9. Okay? Then after that, next step. So going from here to here, from here to here. We took away 1 here, 1 here, 1 here, and 1 here. Now we took away 4, right? And it should be clear to you that in the next one it's going to be 8, because every new interval is going to be where you're going to take one of them, right? So when you take the middle third, you create 2. You create double the amount of intervals. So that's why the number of intervals that you take away duplicates at each step. So first we only took away one interval, then we took away two, then from here to here we take four, and then from here to here we're gonna take eight. Okay, so this one will be 4. And how big are they, the ones we remove here? Well, they're the middle thirds right here. And this one was length 1/9, exactly. So it's gonna be 1/27, right? 1/27, good. And I hope you see the pattern. So what is the pattern? Well, the next one is gonna be 8 of them, and it's gonna be 1/81, which is 1/3 of this one, right? And so on. In fact, it would be better if I write this with powers of 2 and 3. So this is 1/3. The next one is 2 times 1/3 square. The next one is 2 square and 3 cube. The next one is 2 cube and 3 to the 4th. And then it's easy, right? Then I can actually write it like this. It's this series that I think we should be able to do. Is the series 2 to the n divided by 3 to the n plus 1, starting at 0 and continuing all the way to infinity, right? So the power of 3 is 1 bigger than the power of 2 at every stage, correct? Okay, now what is this? We can actually evaluate this one, all right? This is a geometric series. See, I can make it look better if I take away one of the 3's, because then it would look like 2/3 to the power n. And now we know it converges because this number is less than 1, right? 2/3 is less than 1, so it converges. And we even know what it converges to. It's 1/1 minus 2/3, right? Or in general, if this is r, is 1/1 minus r. Correct? Now, what is this? Let's see, this is 1/3 that multiplies 1 minus 2/3. That's 1/3. And the 3 multiplies the 1/3, you get a 1. So the answer is 1. And if this is the first time you're seeing this should be surprising, right? I mean, the things that we're taking away add up to 1. So that means if we're talking about lengths, we started with a length of 1, and the things that we're subtracting add up to 1. So it's like we're taking everything, right? It seems in measure theory terms, you haven't learned about measure theory, I know, but it's a way to measure how what is the thickness of some set in the plane or in space. What we're saying this is that the Cantor set has measure 0, right? In other words, when we're done with this, when we remove everything, there are no intervals in the Cantor set. The Cantor set, it's made up of points there are no intervals there, right? There's no length. The length of the Cantor set is 0, whatever we mean by that, right? If we could define it. So I'm just going to put it here in quotations mark. So this means that the length, I'm putting it in quotation marks because we don't know exactly what that means. The length of the Cantor set is 0. And that's surprising, right? That is surprising. Now, the next thing that I want to tell you about is, well, how big is it in terms of cardinality, right? We sort of see that it's an infinite set. Whatever is going to be remaining has to be infinite, because I already told you that the endpoints will be kept, right? So the endpoints will be there. We know that. But all the endpoints are rational numbers. So right now, we only have countably many. Right now, it seems like the Cantor set is infinite, but it's countable. Is that true? Right? So that's the next question here. Is the Cantor set, go to the next page and leave the picture here. So is the Cantor set countable or not? Okay, and believe it or not, the Cantor set is not countable. It's uncountable. It's as big as the real numbers, right? So even though the length is 0, and it seems like we removed everything, the Cantor set, whatever remains, has the same cardinality as the entire interval. So the answer is no. The Cantor set is uncountable. In fact, the Cantor set and the interval 0, 1, like this, have the same cardinality. They have the same cardinality. So it has as many elements as the real numbers. The Cantor set does. So you may be wondering, how is this possible? Well, I'll tell you why. I'll explain to you a different way to know if an element is in the Cantor set or not. And the idea is to write down the decimal expansion of a number, but not the decimal expansion, because the decimal means we're using 10 digits, right? So we're going to use the ternary expansion of a number, right? So instead of using 10 digits, we're going to use 3 digits, all right? So for the ternary expansion, what that means is that we only have the digits 0, 1, and 2, all right? So if you count with the numbers 0, 1, and 2, this is how you count. You go like this. You go 0, 1, 2, and then the next number after that is 1, 0. I don't want to say 10 because it's not 10. This is 3 in ternary expansion, right? So then it's 1, 1, then 1, 2, then 2, 0, 2, 1, 2, 2, and then 1, 0, 0, right? That's the next one after that, and so on. So this is use ternary expansion. Okay, so you can write any number with its ternary expansion, right? You can, instead of writing its decimal expansion, you can write its ternary expansion. For example, see, what is the ternary expansion of 1/3? Well, 1/3 is exactly 0.1, right? Because these are units, these are 1/3. So when we use decimal expansion, we go by powers of 10. When we use ternary expansion, we go by powers of 3, right? So if you have a number in ternary expansion, so let me write a number like 23.11. I mean, not 23, because we can only use the digits 0, 1, and 2. So 21.1102. What is that number in our regular system? Well, remember, these are 3 to the 0. These are 3 to the 1. These are 3 to the -1, 3 to the -2, 3 to the -3, and 3 to the -4. So this is the number 2 times 3 to the first, plus 1 times 3 to the 0, plus 1 times 3 to the -1, plus 1 times 3 to the -2, plus 2 times 3 to the -4. That's what this number represents, right? So it is 6 plus 1, 7. And then this is 1/3, this is 1/9, and this is 2/81, right? So that number, I don't want to do the addition, but that is the number represented by this ternary expansion. Okay? Is that clear? How you can represent any number?
How'd you get 1/3 equals 0.1?
Well, it's the same thing here, right? So this is the 3 to the first, and this is the 3 to the ones, right? So this is exactly 1.
It would help. Sorry.
Yeah.
Maybe it would help to put like decimal on the left side and trinary on the right side, just to clarify, like we're changing bases.
Yes, so this is 1/3 as in trinary expansion. So usually what is it that people do? They do like this, right? to indicate that it's a number written in base 3. Yes, thank you. So is that clear? This is not a decimal number. When you write numbers like this, what you mean is 1/10, right? 0.1 is just another name for 1/10. That's how the decimal expansions of numbers work, right? So if you think about it this way, you can write down any number between 0 and 1, right? So any number between 0 and 1 looks like 0 point x1, x2, x3, x4, etc. Right? That's the decimal, that's the trinary expansion. And what it means is this, if you want to write it as a precise number, is this, it is x to the I, x sub I over 3 to the I from I equals 1 to infinity, where the xi's are the digits. Their xi's are either 0, 1, or 2. Those are our only possibilities. We only use 0, 1, or 2, right? It's the same as decimal. With decimal, what are the digits you use? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We just have more. Here, we're only going to use 0, 1, and 2, okay? And the reason that trinary expansion is good for the Cantor set is because it explains very well what are the numbers that are left, right? Because think about it. What are the numbers that we were removing? We started with the big Cantor set from 0 to 1. And in the first, so this was C0. And we removed from here to here. What are the ones we removed? Well, we removed everything from 0.1 to 0.2. So the ones we removed are the ones that have 0.1 and then anything else, right? So we remove the ones that have the first digit equal 1. We remove numbers with first digit 1, right? Now, let's go to the next iteration. What's the next iteration? So for the next iteration, we had already removed the middle third. So now it was from like this. And what did we do? What did we do now? Well, now we remove from here to here. And what are these numbers? Well, this one is 0.01, and this is 0.02. And we also remove from here to here. This is 0.21 and 0.22. And these are the ones we removed. So which numbers did we remove? We removed the numbers that look like 0.01 and then stuff. And over here, the numbers that look like 0.21 and then stuff, right? Other digits. So in other words, we remove the numbers that have their second digit equal to 1. We remove numbers with second digit equal to 1. And so on and so forth. If you think about it, that's exactly what we're doing. We're removing all the numbers that have a digit equal to 1, right? So if you look at it, if you look at things this way, the Cantor set, so the Cantor set consists of all numbers in the interval 0, 1 that have no digits equal to 1 when written in base 3.
Isn't 0.1 in it though, since it's left in? So wouldn't it be any that have no digits equal to 1 and then have digits after it that are not 0?
Good observation. Who said that?
And Noah.
Noah, yes. You are good in the following sense. You're wondering, what about 0.1? Didn't you say, Professor, that 1/3 was going to stay all the way? And you are right, but that's because of a different thing. You may remember also from your homework problem that a number has actually two different representations, right? In base 10, you can have a tail of 9s, right? So this is like an aside. So remark, in base 10, you may remember, in base 10, this number, 5.9999999, etc., all a bunch of 9s, is the same as 6. You do know that, right? The tails of 9s take you to the next number, actually. So the same thing happens in base 3. So in base 3, you may be thinking, well, what about 0.1? Well, the thing with 0.1, which is 1/3, is that we can also write it as follows. We can also write it as 0.2222222 forever 2. And that's the reason 0.1 survives, okay? Because you can write it with only 2s.
Do you mean 0.0 and then 2 repeating?
Yes, thank you. Thank you.
Okay,
thank you,
I think
yes.
I understand then.
0.0 and then a lot of 2s. Yes, that's correct. Mm-hmm.
Thank
Yeah,
you.
so that's the reason why 1/3 survives, and that's now why you can tell 1/4 is in the Cantor set, because we can write down what is the decimal, well, the representation of 1/4 in base 3 is actually 0.111111111, right? And that's the reason 1/4 is in the Cantor set. And now, to finalize this part about cardinality. See, so what are then the numbers that survive in the Cantor set? I'll write it down. So based on this observation, we can write the Cantor set as follows. So the Cantor set C is the numbers that you can write as follows, as xi over 3 to the I from 0 to infinity, where xi is either 0 or 2. You only use 0s or 2s. That's the Cantor set. The numbers where you can write as in ternary with only the digits 0 and 2. Okay, and why is this in one-to-one correspondence with the entire interval? Well, the reason is the same way we did base 3, we could do base 2, binary. Binary is more familiar to you, right? So binary is only 0s and 1s. So here, this would be the bijection. So here is the bijection f from C to the closed interval 0, 1. Here's how we do it. Every time you give me a number like this, I send it to this one, xi over 2 divided by 2 to the I. In other words, I change all the 2s to 1s, and then I write it like if it was binary. Does that make sense? So every number that you give me in the Cantor set, it's only made up of 0s and 2s. For example, let me make a specific one. So 0.022020220, where am I going to send this guy? So this one written in base 3, I'm going to send it to 0.01101011101. The only thing I did is changed all the 2s to 1s. That's what I did here. I took xi divided by 2. So the 2s become 1s, and the 0s stay the same. And then I'm writing this now in base 2. So instead of being 3 to the I, now it's 2 to the I. All right? So this is the bijection. And I'm not going to show it's a bijection. That will take me the rest of the class. But I hope you can see it, right? I mean, there's a unique way, well, except for tails of 1s, to write an element in binary here, and obviously it will only come from one of these guys, so it's obviously 1-to-1, and then you would need to show that it is onto as well, but it is. You can believe me. This is how you can establish a bijection. So and that shows that the Cantor set is uncountable. All right. Okay, so let's see. Let's go backtrack. It's a funny set, right? Let's see what we saw. Almost nothing remains if we're talking about length. So there's only some dust, little points here and there that remain. However, those guys make up as many elements as the entire real numbers. So even though it seems like nothing remains, in fact, it's a lot of things that remain. Okay? Now, for yet another interesting thing of why the Cantor set is peculiar. Now, I want to talk about dimension. And I'm not going to define it properly, but I'm going to rely on your intuitive notion of dimension. So here is what I want to talk about. What is the dimension of C, of the Cantor set, right? And let's start by looking for analogies of things. So I'm not going to define dimension. So this is an informal discussion of what we mean by this. But let's talk about things that we know the dimension of. For example, segments, squares, cubes, right? We know a segment is one-dimensional. We know a square is two-dimensional. We know a cube is three-dimensional. We could also use a sphere, right? But squares are better, and you'll see in a moment why. So let's start with. So I'm going to write here the dimension of objects we know. And well, actually, let's write the set here. The set, and over here it's dimension, right? So we start with dimension 1, and we can think about an interval, right? And an interval of length 1 has dimension 1. Then for dimension 2, I can think of a square. A square of length 1 has dimension 2. Right, and if we go dimension 3, now it's a solid cube, right? And that's dimension 3, and that's as far as I mean, I could go dimension 4 and so on. But here's where the dimension sort of makes sense, if you allow me. Okay, so consider this guy and then magnify. So object. Okay, I labeled this one way and then I did the picture the other way. So this is the dimension, and this is the set. Now let's magnify the set by a factor of 3. Magnify by a factor of 3. Okay. So if we magnify this guy by a factor of 3, then it looks like a longer segment, right? A segment 3 times as big, right? And then my question is, how many of the little ones fit into this one? How many original ones fit into the magnified?
3.
Yeah, thank you. 3, right? 3. Okay. What about if I do the square? So if I do the square, so now what I get is a square that is 3 times as big. So now this is 3 times as big. And then if I split it like this, how many of the original ones fit into this one? Obviously, I did not do the picture to scale. So how many of these fit in here?
9.
9, right? 9. And this 9 happens to be 3 square, right? That's kind of where the dimension comes in. If this has 2 dimensions, when I scale it by any factor, I chose a factor of 3, but I could have done it with a factor of 2 or with a factor of 5. It wouldn't have mattered, right? It would be whatever the number you have, in this case 3, raised to the power 2, because the dimension is 2, right? Let's do the cube. So if we make the cube 3 times as big, we magnify it by a factor of 3, we now get a larger cube, kind of like a Rubik's Cube, right? And how many little cubes do we have in this Rubik's Cube?
27.
You bet. So that's 3 to the 3rd power, right? The same as before. Yeah? Okay. Now let's think of the Cantor set, okay? So we don't know its dimension. Let me call it X. And over here, we're going to put the Cantor set. So the Cantor set, can I make a picture? Well, I can try. So it's like this, and then little dusts here, like this, so on, right? That's the Cantor set. And then I'm going to magnify the Cantor set by a factor of 3, right? Now, what happens when you magnify the Cantor set by a factor of 3? Well, before, remember, we started from here from 0 to 1, right? So now it's going to be from 0 to 3, correct? But now think about it. It will be from 0 to 3, and right here in the center, there will be nothing, right? Because this part in the center, the middle third, I should make this to look better to scale, right? So this middle third will come from the middle third of this one here, and there's nothing in here, so this part will be empty. Now this little part over here will go here, right? So this is gonna look like the one we initially had. So this one's like this, and then little dusty thing here, and then here, and so will this one over here, right? See, it's hard for me to draw the picture because there's nothing left, right? I mean, we already said that it looks like nothing. So the point that I'm trying to make is the following, that if you look at this one, how many copies of the original one are in the magnified one? How many copies? So the same question I asked you here, you told me 3, 9, 27. How many? How many of the original Cantor set are in here?
2.
2, that's right. So this part over here is the Cantor set, right? This is exactly the same as C. And this is like a copy of C, only moved 1 unit, 2 units to the right. So these two are exactly the Cantor set. This one over here and that one over here. So we got 2 copies, right? 2 copies. So these 2 copies should be 3 to the something, 3 to the dimension. That's the rule we were using, right? To figure out this answer. We were going, whatever the dimension is, you go 3 raised to that number. 3 raised to the second power, that was 9. 3 raised to the third power, that was 27. So here we're looking for a number x, such that 3 to the x is 2. And that's a weird number, right? The only number that makes that work, so 3 to the x equals 2. If you solve for x, that means x is, so how do we solve for x? We apply logarithms on both sides. So it's ln of 3 to the x equals ln of 2. And then you use properties of the logarithms to take the x out. So this is x ln 3 equals ln 2, which means that x is ln 2 over ln 3. And this number is actually obviously not an integer, and it's some number that is between 0 and 1. It's about 0.63. So believe it or not, there is a way to properly define the dimension of an object, of a fractal in this case. And if we were to follow that dimension, this object, the Cantor set, has dimension 0.631. So in a certain sense, it lives between dimension 0, this is just a point, and dimension 1. It's an object somewhere in between, right? Isn't that incredible and, you know, astonishing in some sense? All right, so those are the 3 main characteristics we wanted to talk about the Cantor set. So how big it is, cardinality-wise, it says it's uncountable, that it has no length, meaning its measure is 0. It's a set of 0 measure, and that it's a fractal with a dimension which is less than 1. The dimension of it is 0.631, this weird number in between. Okay.
Professor?
Yes.
So are all fractional dimensional like spaces, or I'm saying sets, necessary fractals? Or
no, I mean, I didn't define what a fractal is. A fractal should have another property, which is self-similarity, which is kind of like we did here, where a part of it, if you zoom in, it has to look like it has a copy of the original one. But I didn't want to get into that. So there are other sets that are not fractals, which also have dimensions somewhere in between. That's what I yeah. Let me check. Someone asked something else on the chat too that I didn't see. Okay. Okay. So like I said, I mean, all of this is meant as an introduction to the chapter. The chapter is about topology. So we want to get to have properties that allows us to study things like this, objects like this. And we'll start with some very basic ones. So section 3.2, which is now the one we're going to start, is about open and closed sets. So let's get to that. So open and closed sets. And we'll start with the definition, obviously. And what I want to tell you is that the names are kind of unfortunate, because when we think of open and closed, we think of doors or windows, things that we can open and close. And the thing with open and close is that a window or a door is either open or is closed. And for the sets that we're going to be, these definitions that we're going to learn, it's not going to be like that. So if something is open, doesn't mean it's not closed. So that's the little first warning that I should, even before I write the definition, let's put this warning here. So if a set is open, it does not mean it's not closed. And the same thing in the other way around. And vice versa. Or I'll write it again. Similarly, if a set is closed, it does not mean it is not open. And there are some sets that are neither open nor closed. Okay, we're going to learn about that too. So there are some that are neither. But there are sets that aren't closed and they aren't open either. Okay, so let's start with our definition. And before we start with our definition, let me recall something that we were using before, our little neighborhood, epsilon neighborhood. So recall that this guy, the epsilon neighborhood centered at A, was this: the real numbers such that the distance from X to A is less than epsilon. Or if you want, is this interval, A minus epsilon to A plus epsilon. If I were to do a picture, here's a real line. Somewhere there is A, and you go epsilon this way and epsilon that way. This is A plus epsilon, and this is A minus epsilon. You don't include the endpoints, but you include everything in between. That's V epsilon A. All right, so that's just something we saw before, but we're going to need it to make sense of this definition. So here's our definition of an open set. Definition 3.2.1. We say that a set O is open. A set O subset of the real numbers is open if for all A in O, for every point in O, there is some epsilon such that the neighborhood, the epsilon neighborhood centered at A is inside O. It's a subset of O, right? So if you can find a little neighborhood, for every point you can find a little neighborhood where the entire neighborhood is inside the big set, we call it open. Okay? So let's start with some examples and non-examples. Best way to understand the definition is to try it out with some examples. Example number one, the entire set of real numbers. This guy is open. Let's prove it. Let's say that your professor is very mean and he asks, okay, prove it. How do you know the real numbers is open? Well, not to worry. We pick a point. So let A be an arbitrary point in the real numbers. And what I need to show is that there is a neighborhood where the neighborhood is inside the real numbers. Well, that's easy. Just pick any neighborhood. Let A be a real number. Pick epsilon equals 1, just because I like the number 1. And note that the interval B1 around A, that's the interval from A minus 1 to A plus 1, that's obviously inside the real numbers. All intervals belong to the real numbers, are subset of the real numbers. That's what I meant. So of course, this neighborhood is a subset of the real numbers, and we are done. That's it. That's my little explanation, right? So that was a silly example, if you think about it. Here's a not so silly example. How about the interval 0, 1? The open interval 0, 1. Maybe now you see why we call it the open interval. Because it's going to be open, right? Why is the open interval 0, 1 open? Okay, so now it's not as easy, right? Let's do a picture right here. Here's a real line, and we're picking from 0 to 1. So from here, 0 to 1, but not including 0 or 1. That's our 0, 1. Why is this guy as a set open? Okay, what is it that we need to do? We need to show that every point inside here has a neighborhood that is also inside here. So let's pick an element in here. How about this guy, A? So let A be an element of 0, 1. Which neighborhood do you think will work? Which neighborhood around A can we guarantee that we will be perfectly inside here?
1/2 A equals epsilon.
1/2 A, all right. So let epsilon be A over 2, or 1/2 A. Oh, well, let's see if it works. So what about if I pick, so let me try an example. So, and then you want to show that the neighborhood of this big, centered at A, is inside the interval 0, 1. So let's try it. Before I try the proof in general, let me try an example. What about if A is 0.9? So if A is 0.9, then the epsilon you told me would be 0.9 divided by 2, which is 0.45, right? And then are you telling me that if I look at 0.9 and I look at a neighborhood of radius 0.45, I'm going to be inside 0, 1? Is this true?
No, it fails in general.
It's not true, right? Not true. False. So the one you told me is not right. You're almost right. See, I picked a number to throw you off, right? I picked 0.9, but if I had chosen 0.3, it would have worked, or 0.4, right? So why did you pick A over 2? That's the better question. Why did you pick A over 2?
I needed it to land in between 0 and A. And since A is the magnitude of A is, well, itself, just take half of it.
Excellent. And very good reasoning. Yes. So you said from A to here, I need to fit it inside here. So I measure the distance from A to 0, and that's A. So let's go halfway. That's what you did, right?
Yes.
But you forgot the other side. And that's why my counterexample put you in trouble. The same thing needs to happen from A to 1, correct? You need to be inside from A to 1 on the right side. So whatever epsilon you pick should also be smaller than this distance from 1 to A. Yes? And you can also halve it if you want. So the better way is to actually, so here's the correct one. So this one doesn't work. So it doesn't work. But it was a good idea and a good initial attempt. So here's one that's going to work. Let epsilon be the minimum of A over 2. That's the one you chose. And the other one is from 1 to A. So that's 1 minus A over 2. Take the smallest of those two. And then it's going to work. So then we can check. Check to see that the epsilon neighborhood around A is inside 0, 1. It should be easy, right? How do you check that? Well, you need to check that any number that it's in the neighborhood belongs between 0 and 1. All right. I don't want to do it because I want to present other examples, right? And also ones that are not open, right? So so far these two are open. Now we did it with the interval 0, 1. You have to realize that we could do it with an arbitrary interval. So in the same way, let me write it over here. I need a bit more paper. Hold on just a sec. The interval C to D is open, as long as C is less than D. Right? And how do we do it? So again, let's see the picture. So here's the picture. Somewhere there is C, somewhere there is D. We don't include C, we don't include D. We pick an arbitrary element A, and which epsilon are we going to choose? Well, pick the smallest of these distances, right? You don't need to divide by 2, by the way. That was just you being trying to be, give yourself a little space, which is a good practice, I admit, but we don't need it. So here, pick for an arbitrary A in CD, pick epsilon to be the minimum of C minus A or D minus A, right? I mean, A minus C, I'm saying. Otherwise, it's going to be negative. A minus C. So this distance and that distance. Take the smallest of those two, and that one should work, all right? So that's why you know that all the open intervals are actually open, or at least all the open bounded intervals. Now, here's another interesting set that is also open, and for a weird reason. So another example, the empty set. The empty set is open. Why? Well, we call it a vacuous argument, right? Because what is the definition? Let's take a look at the definition. The definition is right here. Something is open if for every element there is some epsilon that makes this happen, right? So what is it that we need to check for the empty set? We need to check that every element of the empty set has some property. But what are the elements of the empty set? There aren't any, right? The empty set has no elements. So because it has no elements, then there's nothing for me to check, right? So the condition is for every element, something must happen, but there aren't any elements. So it's like we don't even need to check. Therefore, it satisfies the definition by vacuity is what we call it, right? It automatically satisfies the definition because there are no elements to be checked. So the empty set is open by vacuity. And I'll provide a little bit more explanation here. There are no elements of elements A belonging to the empty set. So so then we don't have anything to prove. All right. Okay. So let's see a non-example before we get to see our first theorem. So what would be a non-example? Well, a non-example would actually be something like a closed interval, precisely, right? So a closed interval may not be open, or a semi-closed interval will not be open as well. So let's do a semi-closed interval. So non-example. Well, actually, let me start with something easier. A finite set, or a set that only has one element. Non-example. This guy, 0. It's a set that has 1 point, 0. Okay, now why is it not open? Well, it's not open because for this set to be open, I need to show that for every element in A, there's only one, so it has to be 0. That 0 has a neighborhood inside this set, right? But any neighborhood inside this set is going to catch some other points, right? So if little a belongs to capital A, then little a has to be 0 because that's the only element we have. And note that V epsilon around 0 has elements, or is not a subset of 0. Is not a subset of the set that only has 0, right? It's not, because there are other elements in here. If you pick epsilon over 2, so if you go epsilon this way and epsilon this way, so this is negative epsilon and epsilon. Pick epsilon over 2. Epsilon over 2 belongs in here, but it doesn't belong in here, right? Epsilon over 2 belongs to this neighborhood, but epsilon over 2 doesn't belong to 0. So that's the reason this set is not open. See, if you only have one point, it's not open. And it also works if you have finitely many. So if you have like 20 points, it's also not open. Another non-example, second non-example. Let's look at, I mean, we could do the closed interval on one side, but I think that's, well, actually, let's do that one. So what about if it was like this, 0, 1? So why is that guy not open? It looks a lot like the other one we did. What's the difference? The only difference is that 0 is included and 1 is not, right? So where do you think it fails to be open? So what is the A that's going to fail?
A equals 0.
Yeah, it has to be 0, right? Because all the other ones are going to work by the same reason they work here for when we did it open 0 to 1. So if any number fails, it's going to be the 0, right? So let's check 0. So if we pick a 0, if A equals 0, then I can argue that the epsilon neighborhood centered at 0 is not inside 0, 1. How do I show that? All I need to show you is an element that is in here and is not in there. And I'm going to do it in a similar way as the one we did before. Whatever your epsilon is, so this is epsilon and this is negative epsilon, I can find someone in here that is not in the interval. What is that someone that I'm going to find? Well, I'm going to pick someone on the left, right? Because the left obviously is not on the interval. So I'm going to pick this guy, negative epsilon over 2. So note that negative epsilon over 2 is in the neighborhood, in the epsilon neighborhood, but obviously is not in the interval 0, 1 because it's negative, right? It's a negative number. So no matter which epsilon you pick, this fails. This is not a subset of that. Therefore, it's not open, right? Because to be open, that property should work for every point. If it fails for one point, then it's not open. Okay, that's important, the way the quantifiers are set. So for something to be open, every point needs to have a neighborhood. For every point, there should exist a neighborhood around the point that fits inside the larger set. Okay, questions so far? Good, so here's our first theorem, 3.2.1, and it says two things, 1 and 2. 1 says the union of an arbitrary collection of open sets is open. And number 2 says the intersection of a finite collection of open sets is open. And with these two properties, you can now create lots of examples, right? Because, I mean, we already said that open intervals are open. So now you can put together a bunch of open intervals, and that's going to be an open set, right? So if you do 2 open intervals, that's open. If you do a million open intervals, that's open. If you do a countable number of open intervals, right? So for every rational number, you put a little open interval around, then you do the union of all of them, that's going to be open. Same with intersection, right? But with intersection, it has to be finite, right? For intersection, we need finitely many. Okay? All right. So how do we prove this? Let's start with part 1. So we suppose we have a collection of open sets. So suppose OI with I in some index set capital I is open. Let me write it. Didn't like how I wrote it. Let me do it again. So suppose OI is open for every little I in capital I. Now this capital I is telling me how many open sets I have. And remember, it may be infinite. That's why I don't want to do it from I equals 1 to infinity or from I equals 1 to n, because it may be infinite and it may be not countable, right? Maybe this set is as big as the real numbers, okay? So this I is the index set of our collection of open sets. Okay. All right, now we're going to consider the union. So, and just because it sounds nice, let's call the union U. So we're going to call the union U and prove that the union is open. So let U be the union of all the OIs. We will show that U is open. How do we show something is open? We pick an element in U and we need to show it has a neighborhood that is contained in U, right? That's what we need to do. So let's do it. Pick an arbitrary point A in U. Okay, we pick an arbitrary point. Now what? Well, U is the union of a bunch of these guys. So this set A has to belong to one of these, right? So assume that A belongs to OI naught for some I naught. So it has to belong to one of these, right? So I just pick the one that it belongs to. Okay. And then I'm going to use the fact that this guy is open. So because I know this guy is open, I already know that for an arbitrary epsilon, I mean that there is an epsilon that is where the neighborhood around this guy is inside OI0. Okay. So because OI naught is open and A belongs to OI naught, we know there is some epsilon greater than 0 such that the epsilon neighborhood around A is inside OI naught. And believe it or not, we are done because this same neighborhood is going to work. Why? Because this guy is in turn a subset of the union. So I'm just going to write here, we are done because B epsilon A is a subset of OI naught, which is in turn a subset of the union of all the OIs. And that's U. So what is it that we did? Let's recap. We picked an arbitrary point in U, and for that arbitrary point, we show there is an epsilon such that its neighborhood is inside the set U. That's precisely the definition of being open. So U is open. All right. Is that clear? And we have like 3 minutes, so maybe we can do the other one. It's very, very similar. The difference is that now we have a finite collection. So for part 2, suppose that O1, O2, O3, all the way to ON are all open sets in the real numbers. Okay, and then we're going to consider the intersection. So let me call it, I don't know what to call it. I don't want to use I because we used I for the index set. So let's call it K. Let K be the intersection of all the OIs from 1 to N, finitely many. And we need to show that this guy is open. So we pick an element in K. Let A be an arbitrary element in K. Okay. Now, because it belongs to K, it means it belongs to all the OIs. So thus A belongs to OI for 1 less than or equal to I, less than or equal to N, to all of them. And each one of these is open. Therefore, each one of them has a neighborhood, right? So because OI is open, there is epsilon I such that the epsilon I neighborhood centered at A is inside OI. And this happens for I between 1 and N. Okay. And then all we need to do now is to figure out how to make it so that the neighborhood is inside all of the OIs. So each OI has its own neighborhood, right? So which one should we pick so that it works for all of them? So here, the best picture to make it's actually like a Venn diagram type of picture. So imagine that each one of these is an OI. Right? I know that the sets are in 1 dimension, but this helps a little bit, right? And we have someone in the intersection, that's the A. And each one of these has its little neighborhood that works. So maybe the one that works for O1 is this pink one. And the one that works for O2 is this red one. And the one that works for O3 is this blue one. So how do I create a new neighborhood that works for the intersection? And obviously, you quickly realize that the intersection of all the neighborhoods should work. Or maybe if I pick the smallest of these epsilons, right? The smallest of these epsilons, because they're all centered at A. They are all centered at A, right? So pick epsilon to be the minimum of all the epsilons. And this is where the finite thing matters, right? So we're already 1:45, so I'm gonna not finish the proof. We'll pick it up from here next time. But the idea is to pick the smallest of all of these numbers. And this is where it's important that it's finitely many. Because if this list is infinite, then the minimum may not be defined, right? Or the minimum may be 0. And we want epsilon to be greater than 0. That's part of the definition. Okay, so we'll finish it up next time. And we'll continue on Wednesday with chapter 3, section 3.2. All right, I'll see you guys in a couple of days.